So what's up guys, welcome to Venom Pronov Academy, and in this video we are going to look at set operations. Okay, previously we looked at set symbols, but today I want us to look at set operations, and there are basically three set operations that I want us to focus on. Okay, so the first one is intersection. Okay, intersection. Now the intersection of two sets, let's suppose we've got two sets, set A and set B. The intersection of these two sets is simply going to be denoted as A intersection B, and this set is going to list the elements that are common in both sets. Okay, elements that are found in both sets. So if we are supposed to write this in set builder notation, what we can say is that A intersection B is simply going to be equal to X is such that X is a member of A and X is also a member of what? Of B. Okay, because we are looking at elements that are common in both sets. Okay, if we are to display this or to present this in a picture, what we are simply trying to say is we've got these two sets, set A and set B, and this is a universal set, so let's say set A and set B. The elements that we are looking at right now are these elements. Okay, we are looking at elements that are going to be found at this point. Okay, so we are looking at elements that are common to both sets. So now let's look at an example. Let's suppose we've got set A, and set A contains elements 1, 2, 3, and 4, and we've got set B which contains elements 3, 4, and 5. Okay, so if we look at A intersection B, from the description we are looking at elements that are found in both sets, and from set A we can see that we've got 3 and 4, and from set B we've got 3 and 4. So 3 and 4 are common in both sets, so this is what we are going to have in the intersection. So when we look at set operations and we look at the intersection, then this is what we are trying to say. This is what we are trying to communicate. Elements that are common in both sets that you are taken into consideration. Again, something to take note of, this is not only limited to two sets, it can be as many sets as possible that you are taken into consideration, but the idea does not change. Why? Because for whatever sets of whatever number of sets that you've been given, the only thing that you are taking into consideration are the elements that are found in all those sets. Okay, so now the second thing that I want us to look at, the second operation, is union. Okay, remember when you're dealing with intersection, you're looking for elements that are common in both set A and set B, or also and set C, based on how many sets that you have. But when you look at the union, let's suppose we've got the same two sets, set A and set B, then the union of these sets is going to be denoted as A union B. Okay, and this can be written in set builder notation as set A union B is going to be X is such that X is a member of A or X is a member of B. So what does it mean? We are not only looking for elements that are common in both sets, we are trying to get these two sets and put them together and come up with one set. So if we are to display this in a Venn diagram, then what we are going to get is we are going to get these two sets. Okay, we've got A and we've got B. So if we unify these two sets, what we are simply trying to look at is this. We are looking for elements that are common in all the sets. And again, this is not only limited to two sets, you can have as many sets as possible. Okay, the third one is going to be the complement, or let's say we use the same example, that we had in the first question, where set A possessed elements 1, 2, 3, 4, and set B possessed elements 3, 4, 5. If you have to unify this A union B, then you are going to get elements 1, 2, 3, 4, and 5. Okay, this is what it means. You've unified. Of course, you're not writing these two because you're not going to write 4 3s and 4 2s, because you're not going to write 2 3s and 2 4s, because these elements are existing in both sets, so you just write them once. Okay, the third one is going to be complementation. Okay, compliments of the season. So that was just me trying to be, I don't know what I would call that, but yeah. So complementation is one of the operations that we have. Okay, now let's suppose we've got a set E. Okay, that set E is a universal set composing of all the elements, and we've got another set A, and that set A is a subset of E. Okay, so what I'm simply trying to say is we've got this. Okay, we've got this, and this is E, then we've got a set A inside. Okay, now when we say A complement, which is simply going to be denoted by A with this thing in front, or others will write it as A with a C okay, raised to the power c. Then what we are simply trying to say, or what we are simply trying to ask of you, is to list the elements that are not in A. Okay, since A is a subset of E, we are looking for elements that are in E but are not found in A. Okay, so this can be written as A complement is simply equal to X is such that X is not a member of A, but X is a member of what? The universal set. So this is what we are looking for, elements that are not found in A but they are found in the universal set. So this is what it means when we talk, or when we look at complements. Now, the complement of a particular set can also be treated as subtraction. So if we are looking at A complement, this can also be written as A complement can simply be equal to the universal set minus set A. Okay, in short, all the elements that we have in the universal set, we remove all the elements that are in set A. Then the elements that we remain with are the elements that are outside A. So if we say A complement, we are simply trying to ask you to find elements that are outside A. Okay, and this, at some point you realize that it's simply equal to universal set intersection A complement. Okay, but we are going to discuss how we come up to this when we start looking at the set laws. Now, in the last part of this video, I simply want to talk about the different types of sets that we have. Guys, we've got what we call an empty set, we've got what we call a singleton set. So an empty set does not possess any elements, it's an empty or a null set. We've got a singleton set. A singleton set contains one element, just from the word single, so it contains one element. Then we've got what we call disjoint sets, sets that do not have any elements in commons, and disjoint sets are simply going to be written like this. So let's say if we've got set A and set B, then this is a universal set. These are disjoint sets. Why? Because they do not have any elements in common. Thus, there is no intersection, or the intersection of these two sets is simply going to be an empty set. Then we've got also what we call power sets, a set comprising of all the subsets of a particular set, including the set itself. We've got what we call supersets. We've got what we call proper sets. We've got what we call subsets. There are different types of sets: equivalent sets and equal sets. And remember, we said all the sets that are equal, they are also equivalent, but some sets that are equivalent are not equal. Okay, so if two sets are equal, then they're also equivalent. But if two sets are equivalent, it doesn't necessarily mean those two sets are also equal. So please, if you found this video helpful, don't forget to subscribe, to hit that notification button, to comment, and to share this video with your friends. In the next video, we are going to be looking at the laws of sets. Okay, thank you very much for watching this video, and please stay tuned.